Live from Utrecht, this is the Wirdum Sjorsnado.
Hello.
Hey Sjors.
What's up? What's going on?
Ruben is back.
He's back.
Ruben is back. Hello.
Ruben,
Yeah,
did you subscribe to the Wirdum Sjorsnado?
indeed I did. I am a subscriber now.
Nice, because we do have our own RSS feed now.
Awesome.
You can find us in your favorite podcast app. I think this is the last time I'm going to mention it. Sjors, what do you think? Maybe one more time next week?
Well, we have no influence over that because our editor can just make you say whatever he wants you to say.
He'll just edit it in there if we forget, apparently.
That's right.
Ruben, you contacted us last week because you listened to our last episode
That's
about...
correct. Assume UTXO.
That's what it was about. Assume UTXO.
Yep.
And you told us, Aaron Sjors, you're being such idiots. There's a huge difference between assume UTXO and assume valid, actually.
No, that's not how I put it at all.
So you're gonna issue the correction for us now. What is the difference?
No, I just wanted...
By the way, this isn't what the episode is going to be about.
That's right,
But
yeah.
Just to start out, what's the difference? What did we forget to mention?
So there was just kind of one difference between assume UTXO and assume valid that I personally think is kind of interesting, and I just wanted to kind of point that out. And it's not, there's nothing, you guys didn't say anything wrong. It was just something that I thought would be good to, as an addition, basically, to what you guys were talking about. So the specific difference is that with assume valid, you have miners also indirectly saying that the most proof of work chain of headers is a valid chain. And because of that, you kind of have a double proof with assume valid. You have the proof that miners are saying it's correct. Presumably, this is kind of SPV proof security, so it's not something you want to fully rely on.
Yeah, as a quick recap.
Yeah.
And we're not going to redo the episode.
I was going to say, listen to the last episode.
Assume valid is you insert the hash somewhere in the code. Wait, I got to re-listen to our own episode.
Exactly. That would be the best way of doing it.
If that hash is in the blockchain, so it's a block header hash, then you assume that everything that happened before it has valid signatures.
That's right.
So at that point, you're trusting developers that they put in a hash that is in the valid version of the blockchain.
Yeah.
And you're also trusting miners that is in the valid... Wait, yeah, so miners had to actually expend energy to produce that hash.
Yeah, exactly.
And everything that came after it.
Otherwise, it wouldn't be in the most proof of work chain anymore. And then even though, like, let's say in Bitcoin Core, it said, well, this hash, this block, all the blocks before it, all the signatures are valid, but then that specific block is no longer in the longest most proof of work chain.
Yeah, so the thing is, you're not just trusting developers, even though you're kind of trusting them a bit.
Yeah.
And you're also not just trusting miners.
Yeah.
They got to both collude somehow, and that's why it's sort of secure.
That's right.
And now there's assume UTXO, and you're
Right.
saying there's slight difference.
Yeah, so I'm saying with assume UTXO, because there's not an actual commitment to the UTXO set inside of each block, it means that miners haven't really committed to that state. So what that means is that if in Bitcoin Core, you have assume UTXO and there's a mistake introduced inside of that UTXO set, then miners are not going to reject that block because the hash of that UTXO set is not going to be contained within that block.
Right.
So you don't have that double assurance of miners as well.
Right. So the reason I think that's negligible,
Yeah.
that's probably a very mispronunciation of that word.
Negligible. Yeah.
Exactly. Is because the only way to use that to your benefit as a developer, in this case, let's say you're a developer and you create this UTXO set for assume UTXO, and you say, hey, I've actually on my address, I got 1,000 billion million Bitcoins. The only way you can ever benefit from that is if in a block after that, a miner is willing to include it.
Yeah.
So you're still relying on proof of work in that sense.
Unless you find an idiot that sells zero confirmation Lambos. I mean,
Right.
Maybe.
So I guess that would be the one example where it would be a difference.
Yeah. No,
But the zero confirmation Lambo person, you can just double spend. So
Yeah, there are probably other ways to screw that person over. That's true.
All right. So far, last episode, another episode with extra Ruben. This time we're not gonna discuss one of your proposals.
That's
you're just here to discuss a proposal with us. And the proposal we're discussing this week is Utreexo.
That is correct. Yeah.
Utreexo. And the tree is for a tree, the thing that grows in the forest.
So
Did you know that was the pun, Ruben? I didn't realize.
Well, I mean, I heard Tadge say that, so I was aware of that. But there is a very specific reason why I was kind of enthusiastic to talk about it. Well, one, I've kind of like used it in one of the things I've been working on, so I kind of like Utreexo a lot conceptually. But there is also a close friend of mine, Kelvin Kim, who was a regular attendee of the Seoul Bitcoin meetup, who is now actively working on Utreexo together with Tadge. And I told him I would shout out the other guys that are working on the project. Janus Trulsen, which is apparently not a Dutch person. I think he's like German or something. And Nicholas Guge. Hopefully I pronounced it correctly. But those are the four guys that are currently kind of working on Utreexo. Hopefully kind of will eventually get to a point where this can be useful for Bitcoin Core, but we should obviously start explaining what Utreexo is, because we're just talking about the kind of conceptual.
Oh, we got to
idea
keep
right
it
now.
exciting.
Well,
Sure.
really quick, are these guys with DG Lab?
No, that's completely separate. Yeah, there's a MIT. That's I'm not super familiar with it, but that's what Tadge is with MIT. And then the other three guys are just working on this separately, so they're not involved with MIT or DG Labs. DG Labs mainly works on DLC. That's kind of one of their main projects.
Okay. So, Sjors, what problem are we solving?
Problem, challenge. No, so one of the constraints when you're syncing a new Bitcoin node, we talked about sync a couple of times, is the amount of RAM memory you have. Now, it's not a hard constraint. You don't need a lot of RAM, but if you want to sync it fast, you do. And the reason is this thing called the UTXO set. The UTXO set is the list of coins that you own. We talked about that last time, I guess. But every time the new block comes in, what you do is for every transaction in the block, you check if it's spending something that exists, namely, one UTXO. And so in order to check if something exists, well, it has to be somewhere. It has to be in a database of sorts. And where is that database? Well, if that database is sitting in your RAM memory, that's extremely fast. If on the other hand, that database is sitting on your hard disk, if it's an SSD drive, it's meh.
What you mean is it's much faster to look up if it's in there.
Yes.
If it's in your RAM, then your computer will be able to look it up within, well, I don't know how fast,
I don't
but
know
faster than if it's on your drive at
it's
least.
probably at least 10 times faster than if it's on your SSD drive.
Right.
And if you're using a magnetic drive, it's even worse.
Yeah.
And then the other side of it is once you create this new coin, which the transaction does on the output side, it has to store that. So it has to write it somewhere on the disk.
Right.
Which is also slow. And if you have a magnetic spin disk, then it has to move to read somewhere and it has to move somewhere else to write again. And these are gigabytes apart. So that's horrible.
So to make it very concrete, I guess the biggest difference you would notice when you're syncing a new node, and if you would somehow be able to keep the UTXO set in RAM, it will only take, I don't know, a couple hours.
But it depends on your computer. I have a somewhat recent MacBook Pro, and I think I can sync the whole chain in 5 hours.
If you keep it in RAM.
But that takes about 11 gigabytes of RAM. But if you do it on, say, a typical Raspberry Pi, you might have, I don't know, 2 gigabytes these days, maybe 4. So that means you're going to sync the chain, and you're going to keep as much as possible in RAM, but at some point it overflows the UTXO set. And then usually what it does is it writes everything to disk, clears everything, and then it starts caching again. And this takes a long time. Like, it can take days on these machines.
Right. So the point being, as you can keep more of the UTXO set in RAM, you'll sync faster, or your node will just work faster, operate faster in general. So it would be good if we could somehow decrease the size of the UTXO set.
Well, we can't decrease the size of the UTXO set. That's kind of the problem.
That's a bummer.
There is a limit on the size of blocks.
Well, it can decrease.
4 megabytes.
It can decrease. It's just not something we can do.
Yeah, it decreases when people spend.
I don't know how much UTXOs you own, Sjors. I bet a lot. So maybe you could play a part in decreasing the UTXO.
I own millions of UTXOs on testnet. No, so the idea is that if you're spending more coins than you're creating, then obviously the number of UTXOs goes down and the RAM usage goes down. But there's a lot of junk in the UTXO set, because there were people in the old days that created transactions to like multi-sig addresses that were fake just in order to put pictures of Obama in the blockchain. And those are all sitting in your RAM because your node has no idea that they're nonsense. But the other thing is, if we expect everybody in the world eventually to use Bitcoin and everybody to have at least, 1 or 2 UTXOs, then, well, that's a lot of RAM. That's like 7 billion people. And there's really no limit to how big that can get. There's no constraint. It might take a while because it takes a lot of fees to create all these transactions, but eventually it could take as much RAM as, there's no limit.
Yeah,
we don't like things that don't have a limit. Unbounded stuff, it's a bit bad.
Yeah.
Yeah, you mean the UTXO set can get as big as it will get until the point where not everyone can use it, can sync it from RAM.
Fewer and fewer people will have enough RAM to sync it quickly, and that could become a problem, right?
Okay, so you agree it's a problem, not just a challenge. It's a problem, Sjors. Now, how do we solve it?
No, it's a challenge, obviously. Well, one way to solve it is Tadge Dryja's proposal, the Utreexo.
Right. Yeah.
And the idea there, I guess that's what we'll need to explain, right? How that works.
Well, Ruben wanted to explain it to us.
Well,
so let's hear it.
I first wanted to say that I thought, Aaron, your analogy with basically saying that it's pruning for the UTXO set, I thought that was a very good analogy where currently we have pruning in Bitcoin.
This was an off-record analogy.
Yeah.
Currently, but now it's an on-record
Now
analogy.
It's on record, yes. I'm repeating something that you told me before the show. So with Bitcoin, currently you have pruning in the sense that you take a block, you process it, you extract the UTXO set out, basically from all the blocks, and then that's all that you keep. You only keep the UTXO set, and then you can throw everything else away, and that's called pruning. There is a downside, which is that then you don't have the blocks. So if you want to prove to another person that the UTXO set is valid, you can't actually give them the blocks, but the assumption is that somebody else will have the blocks, so it's fine. And here, what you're pruning is something else. You're pruning the UTXO sets, and you're essentially taking out you're throwing away all the transactions, and you're just keeping a Merkle root. And inside of that Merkle root is basically a commitments. Every single UTXO is committed in there, and you only keep the Merkle proofs of the UTXOs that you care about, that you own.
What is a Merkle root?
Yeah.
Or maybe to put it another way, normally when somebody sends you a transaction, the transaction says, I'm spending this input, and you, as the person running the node, has the responsibility to check whether that input exists in your own database. And you're flipping this around, and you're telling the other node, I have no idea which coins exist, because I don't have RAM. You proved to me that this coin actually existed.
Yeah.
And that's what you use this Merkle proof for. So the burden of evidence is reversed here. You need to prove that a transaction exists. And then the question is, how are we going to do that?
Okay, so we're reversing the burden of proof. Usually when you're sending a transaction, when I send a transaction to you, Sjors, then you check inside your node in the database with your UTXO set whether the transaction is spending valid UTXOs.
Yes.
Now, I'm actually going to have to provide you with the proof that my transaction is spending existing UTXOs. However, you still need something in order to make sure that my proof is valid. And that's this Utreexo, which is a hash tree.
Yes, a
Merkle
Merkle
tree.
Hashes.
Right. So what is this and how does it work?
So it's kind of nice. All the UTXOs that are in existence would be put into this tree. And everybody can construct this tree if you replay the whole blockchain. But the question is...
It's not an actual tree, though, is it, Sjors?
It is not an actual tree.
Do you give it water?
No. It basically, what the tree would look like is you have the first UTXO and then the second UTXO right next to each other. And then you take the hash of those two, basically combined. And that is one new hash. So you see this little pyramid shape. And you can do that again for another two UTXOs that exist. They're their own little mini tree. But now you see, there's two trees. Let me just combine those two trees.
Two hashes, and you're combining these two hashes.
Yeah, so now you have 4 UTXOs, and they two of them are shared, and then those two are shared again.
Yeah, so you end up with one hash.
You end up with one hash. Now, the key here is that these things are so-called, I believe, perfect trees, which means that they are always a multiple of 2.
Right. Yeah, and so now the challenge is that for every new block, this tree needs to be updated, right? Because we have one big tree for all of the UTXOs. Now a new block is found. It includes all sorts of new transactions. So new UTXOs exist and old UTXOs are destroyed. So now we need a new tree.
Yeah, well, it's even more than one tree, right? It is a forest. Because this thing has to be every tree has to be a multiple of 2. So there can be 4 things at the bottom, or 8 things at the bottom, or 16 things at the bottom. When you have a number of transactions that doesn't fit that way, you'll have multiple trees that look like that. So you have a collection of trees for which you really only need to remember the top hashes.
Mm-hmm.
And now the question is, how do you add something to that tree?
Yeah, so you might have one tree with 16 at the bottom, one tree with 8 at the bottom, one tree with 2
One at the
UTXOs at the bottom, or what? Yeah, exactly. So you have multiple trees.
Yeah.
Right. And now, in order to prove that something is in this tree, and also to replace it with, say, the output, because you destroy one UTXO that you're spending and you create a new UTXO that you're creating. So you can actually take the UTXO that you're spending out of the tree and then put the new one into the tree.
Yep.
And in order to do that, you need to recalculate the tree, and you do that by knowing its neighbors. So the way you prove that something is inside a Merkle tree is to say, well, at the bottom of the tree, there's these 2 pairs, and I'm going to give you the other side. And then at the next level, there's a pair, and I'm going to give you the other side, and again and again and again. And that proves that something is actually in the tree. And that's exactly the same information that you need to put something else at the bottom of the tree.
Right.
Yeah,
And
that's
then provide the new
So
hashes.
by putting something else at the bottom of the tree, to be clear, the entire tree changes, or at least the one hash you end up with changes. Like you're just computing a whole new tree. But
Yep.
you're able to do that because you have all the data you need.
Yes.
So you can add things to the forest and you can remove things from the forest. It's actually possible. It's actually easier than I thought it would be when I saw Tadge explain it. I don't know if it's going to be easy when people hear us explain it.
I would
but-
recommend looking at Tadge explain it after you hear
Yeah.
us explain it
And-
poorly,
and-
because it you need to see it and
Yeah,
then you need to
visuals.
understand it.
Visuals really help.
exactly.
with
I
this.
think his presentations are great. He's very good at explaining it, and he has slides, so that's a lot easier than what we're doing. We're trying to explain it in words, especially in Merkle trees. I think it's great if you have a actual picture there.
But now the idea is that you're not tracking everything, right? So you could, when you're syncing the blockchain, keep track of the entire tree, but then you need a lot of RAM, just like in the original scenario. But what you'll actually do is you're going to remember the top of every tree, and there might be 10 or 20 or whatever trees, and that's all you're going to remember. And when somebody has a new transaction that you want to verify, they need to give you the Merkle proofs for all the inputs that they're spending.
Yep.
So they prove that they exist, and then they also tell you which outputs are there, which are going to be swapped in at the same places where those inputs were, plus new trees if it's making more.
The outputs are in the blocks, right?
Yeah.
Yeah, so that's really, I think, the very elegant side of Utreexo, where the same proofs that are proving that these UTXOs are in the UTXO set are also exactly what you need to remove them from the set, update your root hash, and add the new UTXOs from the latest block. So that works out quite elegantly.
Okay, so in an ideal scenario, let's say what we've been explaining so far is sort of the ultimate version of Utreexo. So let's stick with that for a minute. So I wanted to send a transaction to the network, and you, Sjors, you had a node and you wanted to validate the transaction. You have this tree in your RAM, apparently.
Yeah.
That's what's nice about
The
it.
top of the trees
The
in my
forest, yeah, you have to. Yeah, exactly. So now I want to send this transaction. So now it's my responsibility to send to you the transaction as well as the proof that the transaction is valid, which also includes information for you so you know where to find it in the forest, right?
Exactly. You need to prove to me that the things you are spending are in the forest, because I forgot what the forest looked like.
Right. All right. So that's me sending the transaction with the proof. Now, the other way you could get the transaction is if it's already in the block. So if a miner mines a block and the transaction is in there, you still have your UTXO thing in your node, but how do you now get the proof?
Right, because if you spend the transaction, you're not going to talk to every node that ever downloaded the block to send that proof around. So how does that proof get to the node?
That wouldn't scale very well, at least.
No. Well, what you would probably want to have is something called a bridge node.
A bridge node.
A bridge node would be a node that has the actual UTXO set the old-fashioned way, so it has lots of RAM, or it's just slow, and it produces all these proofs, and it sends them around to whoever wants them.
Yeah, so what essentially happens is that when this bridge node receives a transaction, and this transaction does not have a Merkle proof proving the inclusion in the Utreexo root, this bridge node basically just takes the proof that they have and they attach it to the transaction, and now they send it on to other Utreexo nodes. It's a bridge between Utreexo nodes and non-Utreexo nodes.
Right.
Yeah, but they
because
could
nodes-
also construct the proof themselves, right? If they see a certain transaction is included in the block, they can just
That's right. Every node, there's nothing secret here. So if you have the original UTXO set in memory somewhere, you can construct a proof for any transaction.
And they have the entire tree, essentially. So the entire Utreexo tree that you create and then prune, they just don't prune it, essentially. So they just have the full Utreexo set, basically the UTXO set with all the Merkle proofs connecting to it. So then they can just take any UTXO in there and create a proof from it and just send it on, or for an entire block or whatever.
Yeah. Right. So what would happen in practice, Sjors, is your node would see a transaction in a block and it would wonder, is there actually proof for that? I never saw the transaction before.
Well, my guess
is you would request it from a bridge node.
Yeah, my guess is you would, when you get the whole block, you're going to call a bridge node and say, give me the proofs for that entire block.
Oh, just all of them?
Yeah.
I think
why not just the ones you need, the ones you haven't seen before?
My guess is that's too much back and forth. Because if you have to call a node for every single individual transaction, then that's a lot of overhead. Right. Whereas just downloading a couple hundred kilobytes is easier.
That's an implementation detail.
Yeah, but I think this is just an automated process, right? Where you just connect to the network. But like the problem is like when you're the first Utreexo node, right? And you're pruning all the data, and then everybody else on the network is an old-fashioned node like the way we run it today. Nobody's going to give you the proofs, right? So what you need is at least a single bridge node. So at least you can connect to that one. And then other people are connecting to the bridge node because the bridge node basically speaks both languages, right? They speak the UTXO language and they speak the old-fashioned language.
Yeah.
So they translate for you. And as long as one bridge node exists, it kind of can bootstrap the network essentially. But they don't have to have like special rules. It's like from the perspective of the UTXO node, the bridge node is just also a Utreexo node. And from the perspective of the old-fashioned nodes, it's just an old-fashioned node.
Right, that's another point. So, yeah, you don't need everybody to do this translation.
Yeah.
Only one person needs to do it, or a couple. The other nodes know how to relay that information, even if they can't produce it. So that's good news. But of course,
can we have a future without bridge nodes?
Well, we should point out what the problem is with these bridge nodes because they are nice people. We don't want to like rely on nice people. That's not how we roll.
Yeah.
So because nice people can stop being nice.
Or they can be forced to stop being nice.
Or they can just disappear or run out of battery. Yeah. So yeah, then you can look at the longer term picture. Like, could this, if people like this, given the advantages, or even if they don't like it, if the UTXO set just becomes insane and it just takes too long to sync on any normal computer, then you could basically make a soft fork which contains the proofs. So the proofs become part of the blockchain. Just like Segwit added a whole bunch of data to blocks, you could then add these proofs to the blocks, making the blocks even bigger.
Right.
But the trade-off there is you have more bandwidth, but you have less RAM need. So
yeah, and the reason this could be done as a soft fork, same with Segwit, is because you'd include the hash of the proofs somewhere in like the Coinbase transaction or something like that.
Exactly.
Yeah. Old nodes just won't notice anything interesting, but upgraded nodes will see like a whole tree which they share with each other, which does make the blocks a bit bigger for them.
Yeah, so old nodes keep doing what they're doing. They get blocks, they can verify those blocks because nothing changes about the transactions in the blocks. New nodes will save some RAM memory. They'll use that extra data. They'll download that extra data and they'll use it. That's generally the idea.
Yeah. So I like personally, at least, I think this is not likely to happen until we really get a UTXO set bloating issue where the UTXO set becomes so big that people start liking this trade-off to the point where it's preferable. I think as long as we're not at that point, I don't think we'll see this as a soft fork, but that's my personal view.
I do want to point out some cool things you can do with it.
Yes. Tell us the bullish part.
I'm all just copy-pasting from what Tadge said. We like to do that. Basically, because you don't need a lot of RAM, you can start doing things in specialized hardware like an ASIC. Because one of the things that's kind of hard to do in an ASIC is lots of memory. And having specialized hardware, maybe it's a part of your chip. So maybe, Bitcoin becomes the standard and every phone that you buy has a CPU, has a little mini processor right next to it that just checks all the Bitcoin validation rules. And because it's custom silicon, it might be able to validate the entire blockchain at the speed that it can download it, which is pretty cool.
An ASIC for regular nodes.
Exactly. Yeah.
Right.
So not to mine coins, but to verify coins. which would be cool. And then, you have the protocol literally set in stone, or at least set in silicon. And of course, soft forks can still happen under that circumstance. But if somebody wants to do a hard fork, you'd have to break all the node hardware, not just all the mining hardware. So that's a nice extra barrier to not do hard forks.
It's an ossification
It's also
of
not
network.
It's also not perfect for software. Is that what you just said, Ruben? Or
No, I mean, that's what, no.
Well,
That's
it makes
what
it harder
Sjors
to
said.
verify soft forks, because if you don't have to verify the software, but you soft fork, but you can't verify the soft fork, at least not with the accelerated hardware.
Yeah.
So your computer would have to slow down to check all the new rules whenever it encounters it.
yeah, or you'd have to buy a new phone because the soft fork happened.
Exactly. Yeah. Well, that's
Your phone is too old. Maybe it's possible, right? That's what happens now. People buy new phones every couple of years, so maybe it's not too much to ask.
Yeah,
The other thing is, we talked last week about this assume UTXO thing, where one of the problems is now when you start, you still need to get that 3 gigabyte thing from somewhere. And if this thing becomes 100 gigabytes, you have to get that from somewhere. But now with this proposal, we just have a kilobyte. So you can put the entire UTXO set, you can represent it in a kilobyte, which can just be inside the source code.
Yeah.
So, you don't need a hash to then go and fetch something. You just put the thing itself in there. And nodes can start instantly at that height and then do the same thing that we described last week, right? So sync all the way to the tip and then start the genesis and make sure everything is what it should be.
Yeah, that's a really nice kind of feature that you have the entire UTXO set in essentially a single hash or a forest.
Yeah, a small little forest of
1
hashes.
kilobyte. Yeah.
And then
What's not to...
you can also sync
Are there
to
more
your-
benefits?
Yeah, so the last one would be you could sync with a phone node. So right now, if you have a node on your phone, it might be very slow. Maybe with this proposal, it wouldn't be slow, but let's say it's still slow. What you would do is you sync your node on your desktop or whatever it is. You scan a QR code, which can be pretty long, and now your little phone has the recent UTXO set. And that doesn't even require any kind of commitments, right? Because your phone trusts your laptop. So that's a feature you could use right now.
Yep.
Are there any downsides or risks? Ruben, you thought about this.
Sure, but I want to add one more interesting feature that we haven't discussed yet.
Before we burn it all down.
Before we burn it down, yeah. It's a good question, though. And that's parallel validation. So what you can do is you can theoretically take 2 computers and just take a Utreexo hash off the middle state of the blockchain. So, if we're at block 2000, you just take block 1000 and you take the Utreexo hash from that moment in time. And then you start validating 1000 to 2000. And on the other computer, you start validating 0 to 1000. And if they match up after you validated both, then you validate the entire blockchain while splitting up the work. And that's interesting and can be very useful, I think, maybe in the future also when you have like more and more CPUs on a single chip.
Right, so it wouldn't be necessarily multiple computers doing this, but just multiple chips doing it.
Right.
Because we see that clock speed is not going up much.
Yep.
But you get more and more parallel stuff. And the problem with the Bitcoin chain is you can verify signatures in parallel, and the Bitcoin node does that. But some things are intrinsically serial, so you cannot verify block 10 before you've verified block 9.
Right.
And it's nice if you can get rid of that.
Yeah, so now you can, essentially.
Yeah.
And
you can too with assume UTXO, but you need like multiple very large snapshots.
Yeah, exactly. Yeah.
So, yeah, very cool stuff. So, let's burn it down.
Right.
Go for the kill, Ruben.
Yeah, the one more thing to add is apparently you can also do backwards validation. I'm not sure exactly how it works, but apparently you can go from block 1000 to 999. So so that's possible too.
Well, you need to, because you need to be able to roll back.
That too, yeah. So I just haven't looked into that sufficiently to fully grasp it. But
we just explained that in order to prove that something is in a Merkle tree, that's the same thing you can do to change something in a Merkle tree. So you can change the old thing with the new thing that way, or you can change the new thing with the old thing.
Right. Yeah. So it makes sense. I agree with that. I just haven't sat down and just gone through it.
One other thing we can also mention is that this tree that we just described is the general name for it is an accumulator. It's something that you can use to add stuff to, and in this case also remove stuff from. But there are all sorts of mathematical tricks you can deploy to do this. This is something that's conceptually simple. I mean, if other people than us explain it and you see it in front of you, it's very simple with the Merkle trees. But there's been other proposals, like an RSA accumulator.
Right.
And there's all sorts of cool cryptographic math you can do to just add things to a set and remove them from a set, essentially.
Yeah. Yeah, and that's
Perhaps another mechanism would be used eventually.
right. And that's maybe also one of the downsides that we can talk about now, where if you start using this and then later somebody finds a better accumulator, then you have to yet again switch to that next proposal, which is okay as long as you don't commit it into a block. But once you make this an actual soft fork, and then you find, oh, there's this even better accumulator that we should have been using, now you're kind of stuck because you can't undo a soft fork, at least not unless you put in some kind of sunset date or something. But that's generally not really done, at least hasn't been done so far.
No, so that's another reason why you wouldn't expect this to be a soft fork unless like the world is burning or it's been used for so and so long that people think, okay, this is mature.
Yeah.
But we're nowhere near that. It's pretty experimental, as many of the things we discuss here.
And I guess the second thing that I consider a downside is that bandwidth seems to be pretty much the bottleneck right now for Bitcoin. And this is something that makes that bottleneck worse. So for that reason, I personally see this as kind of a more of an option that people can opt into if in their case, bandwidth isn't a problem, but they're CPU or disk IO restricted or RAM restricted, or maybe they want to use an ASIC or something like that. So in that, from that perspective, I don't expect everybody to use this, but I also think Sjors pointed out correctly that if the UTXO set grows to a significant degree where it does become a burden and it slows down validation, then maybe this becomes more appealing.
Yeah, so keep an eye on it.
Yeah,
and I guess the increased block size in one of the variants could be considered a downside. Although I think
that's what we meant with more bandwidth. Basically.
Yeah, exactly. Yeah,
that's yeah. Just
okay, fair enough. Then I guess that's it, isn't it?
Let's see if I had anything else on the list. Nope. I think that's it. Thank you for listening to the Van Wirdum Sjorsnado Special Somsen Edition.
There you go.
There you go.